Alright, so today we're going to be talking about probability. We won't go too in depth with too much probability, but we are going to go past what you probably did in geometry. Today is kind of a welcome back to probability. So to start off with, we're going to be talking about sample spaces. So what a sample space is, it's basically the set of all possible outcomes. So all possible outcomes that are all equally likely to happen. So in this class, we're just going to be talking about things that are equally likely to happen. There are some examples on my slides if you want to look at probability functions which change up the equally likely. So for instance, if you wanted to see the probability of a loaded die, so basically one side of the die is heavier than the other, so it more likely lands on, say, a 6 than any other numbers, so forth and so on. We're not going to get into that for this, but just so you know, that is something that's out there. So an event is going to be basically a subset, so a small portion of that larger sample space. So an event that is happening, so we care about how many different ways can this event happen, and we care about the total amount of outcomes, the sample space. So your probability of an event happening, so probability of an event, is going to be equal to that total number of events over the total sample space. So another way you can kind of think about this is part over whole. So something you've been doing in math for any kind of fractions, it's always part over whole to find the percent of something to happen. But we're not multiplying this by 100 to give us a percent. So probability and percents are really close to one another, except we don't multiply by 100 to get the percent. So that decimal portion of part over whole gives you the probability. So the probability of something to happen. So this is what we are going to be doing today. So I'm going to teach you a couple different ways of thinking about how to find the total sample space, how to find the total number of events, because there's complicated ways, there's easier ways to think about things. So we're going to start with the very first example on the slides, which is find the probability of rolling a sum divisible by 3 on a single roll of 2 fair dice. Okay. So what I am looking for is I care about things that are divisible by 3. So that would be 3, 6, 9, and 12, because I'm only rolling 2 dice, and each dice only has 6 sides. So the first thing we want to try to think about is how many different outcomes could I possibly have? So the nice thing about this is we can go back to that the fundamental principle of counting, or the multiplicative principle of counting, where that just states that if you have 2 different things that are happening, it's simply going to be how many different ways the first one can happen times how many ways the second one can happen. So by multiplying these 2 things together, I get 36. So there are 36 different ways I can roll 2 dice and have different outcomes. So you have to think about where, yeah, you can get a 4 by rolling a 1 and a 3, but you can also get it by rolling a 3 and a 1. So you have to think about each die as a separate entity when you're trying to calculate how many different ways could this happen. It's not just, oh, a 1 and a 3 is going to make 4. Yes, but that actually happens 2 times. Where you could also roll a 2 and a 2, but that's only going to happen 1 time, because there's only one way to make 2 on each of these dice. So this is why that multiplicative principle of counting is very helpful for us. It's just how many outcomes times how many outcomes. There's 6 sides, so I multiply those each together. So now I have to think about all the different ways I can get these numbers. So let's start off with the easiest one. So let's look about 12. So the only way I can get 12 is if I roll a 6 and a 6. So that means there's only one way for me to roll a 12, where both dice have to be 6. So looking at a 9, how many different ways I can get 9? So I can roll a 6 and a 3. I could also roll a 3 and a 6, so each side is the different die. So I could also do a 5 and a 4, and a 4 and a 5. So these are the only ways I can roll a 9, and there are 1, 2, 3, 4. There are 4 different ways to roll a 9. So for 6, we can do the same thing. We have a 5 and a 1 and a 5. We have a 4 and a 2. We have a 2 and a 4. And we have 3 and 3. So as you can see, basically each one has 2, a 5 and 1, 1, 5, 4, 2, 2, 4. But the 3, 3 is only happening one time because there's only one way to roll each of those. So counting up those, I have 5 ways of rolling a 6. And then for 3, it's going to be a 2 and a 1 and a 1 and a 2. So I only have 2 ways of rolling a 3. So these are all of my events that I care about. So each of these is one event. So it's one of these sample spaces of these 36 that I care about. So this is my event. So I just have to add up all of these and I get 12. So 12 out of 36, we can simplify that fraction to be 1/3. Which means that if I roll 2 dice, there's a 1 in 3 chance that it is going to be a 3, 6, 9, or 12. If you added them together, which is kind of nice, I guess, depending on what you wanted to do with that information. So the way we're going to be trying to think about this is how many different sample spaces do I have, so the total amount of outcomes. So there's other ways other than this multiplication principle to be able to come up with this. And then we have to count each of these events to try to see how many total we have. So let's look at the next example. So the next one says a red die and a green die have been rolled. What is the probability of the event? The number of the red die is greater than that of the green die. So again, we're rolling 2 dice. So I know that 6 times 6 is going to give me 36 as my sample space. So there's only 36 possibilities. So now what I'm going to do is I'm going to be comparing the red die versus the green die. And I want the red die to be greater than. So I want my red die to be greater than. So I need to come up with all the events and count how many times that actually happens. So let's start off with red being 6. So if red was 6, that means we can have the numbers 1, 2, 3, 4, and 5 for our green die. So that means out of here, our event being true, I have 1, 2, 3, 4, 5 different outcomes if red was 6. So then we need to check if red was 5. So if red was 5, then green can be 1, 2, 3, and 4. So that means there are 4 different ways. And we can keep on continuing this trend. And there's nothing to be less than 1, so there's nothing here. So all I have to do is now count up this, and I get 15. So there are 15 different ways that it could possibly be my red die being greater than my green. So that means I have a 15 in 36 chance of that happening, which is almost close to a half. So almost half, which is pretty good. So the next slide, if you wanted to look at your slides, is about the probability function. So again, I'm not going to go into that. that was just like an extra thing I did. So that is if you cared about loaded dies, and you can actually come up with some function that gives you each outcome. So you can skip that. Alright. So again, you can kind of see we have almost like a basic strategy. First, it's try to see how many total outcomes you have, so finding your sample space. And usually you can do this fundamental principle of counting, that multiplication principle of counting, by just multiplying the outcomes of the first die and the outcomes of the second die, so forth and so on. And then we were looking for our sample space, so we kind of like tried to figure out how many different ways we can do each one. So we kind of set up some kind of visualization to help us figure that out. Alright, so let's get into some better ones. So Sal opens a box of a dozen chocolate creams and generously offers 2 of them to Val. Val likes vanilla creams the best, but the chocolates look alike on the outside. If 4 of the 12 creams are vanilla, what is the probability that both of Val's picks turn out to be vanilla? All right. So we have 12 chocolates, and we have 4 that are our vanilla that we want. So we need to figure out, and we can only choose 2. So we're trying to take 2 of them. And we want to see what is the probability that the 2 that she takes are actually the 4 vanillas. So I'm going to do this problem twice. I'm going to show it to you one way and then show it to you another way, and you can choose which one you are more comfortable using, which method. Alright, so first off, I need to try to figure out what my sample space is. I need to figure out what the total outcomes could possibly be. So I'm trying to take 2 chocolates out of these 12 chocolates. So of these 12, I'm trying to choose 2 of them. 12, choose 2. Because I don't care about the order that I got the chocolates in. I just care that I got these 2 chocolates together. So my total outcome is going to be 12, choose 2. So of the 12, I'm just trying to choose 2 of them. And that is going to give me all the different ways that I could get 2 chocolates. So we can put that into our calculator. And you get 66. So then I have to try to figure out what my event is going to be. And I want 4 of the vanillas. But how many different ways can I take 4 vanillas? So this is another choose problem, because it allows me to see all the different combinations of me picking those 4 vanillas. Otherwise, you would need to make a list again and try to maybe name each vanilla as A, B, C, and D and figure out all the different ways you can get those. But again, the order doesn't actually matter. So my event is really just going to be 4, choose 2. So 4, choose 2 gives me 6. So that means there is a 1 in 11 chance that Val gets 2 vanillas randomly by picking 2 of them. So this is one way to think about this, is by using our combinations, because we're trying to figure out how many combinations of these 4 vanillas can I pick. And here it's how many combinations of these 12 chocolates I could pick. Otherwise, you're trying to create something that has 66 different ways that you can pick 2 chocolates. So you would have named all the chocolates, try to figure out some way of calculating that. But we've already done this math previously. So this is one way of solving this problem. So the other way is the multiplication principle of probability. So not counting, but probability, but they're actually the same thing. Basically, what it's saying is that if you have an event A, so the first event, and you can figure out that probability, And you can then figure out the probability of the second event happening. All you have to do is multiply those two events together, and it actually gives you the total probability. So what that is so if I wanted to know my event A, so event A is I'm just trying to take one chocolate. So this is my first attempt. So what is the probability of picking a vanilla? So my total sample space is 12 because there's only 12 chocolates for me to go in, reach, and grab. And how many total different things do I have? Well, there's 4 vanillas. So probability of B, so your probability of B is going to be that A has already happened. So we have to now think, hey, A happened, and it happened in the good way that we want it to happen. So we're saying, hey, we already picked, and one of the picks we picked was a vanilla. So now I'm trying to figure out the probability. So I've already done one pick. So that means that I now only have 11 chocolates, and I only have 3 vanilla now, because I've picked one already. So event A already happened, so that means that it was good. It actually happened. We got what we wanted. So now I'm trying to do that same probability again that it already happened. So now I only have 11 total chocolates, and I only have 3 that are what I want. So I can multiply these things together. So doing this, we get 12, and we get 136. All right, 132. So this is also 1 over 11. So these are 2 different ways you can think about it. This, in my opinion, is a little bit easier to wrap your head around because you're taking it step by step. You're saying, okay, here's the first thing that happened. And that's simply going to be, I have 12 chocolates and I'm trying to pick 4 of them. So 4 out of 12. Then the next one, hey, this event already happened and I already picked the vanilla that I wanted. So now I only have 11 total chocolates and only 3 vanilla. So I can then just multiply those fractions together and I get the same exact outcome that we did when we were doing our choose. So this is probably a lot easier to wrap your head around, but know that you can also do the choose method, which is maybe a little bit quicker if you wrap your head around it. Okay, good. All right. So there's some visual ways of doing probability. So we're going to look at Venn diagrams quickly. So all of you probably have done Venn diagrams at some point in your life doing some project or whatnot where you were comparing items. So this is actually a really good method if you have percentages of things and you're comparing 2 things. It's a great way to figure out all the different subsets. So first, let me draw my Venn diagram. Alright, so the first question to you, how many different spaces do I have in this Venn diagram? If you answered 3, you're wrong. Because not only do I have this space, and this space, I have the outside space as well. So there's actually 4 things that are going on in this Venn diagram. And that's kind of what we want. We want 4 different outcomes when you're comparing 2 events. Because it's either going to be a yes and a yes and a no and a no, a no and a yes. That's 4 different things. It's either you do it or you don't. So in this example, we have in a large high school, 54% are girls. We know that 62% of the school plays sports. And it says half of the girls play sports. Alright. So when you're working with Venn diagrams, you always need to go and label your two circles. It's going to help you understand what all these overlaps actually mean. So I'm going to, since we only know girls and play sports, I'm going to label my circles as girls and play sports. So anything inside of the circle is a true statement. Anything outside of the circle is the opposite. So what that means is that this 2 right here is contained in girls and contained in play sports. So this is girls who play sports. So our outside, so we are both outside of girls and outside of play sports. So what that means is it's going to be a subspace that is not girls and not play sports. So this is the combination of both. This is the combination of neither. So we know that a total, so this entire circle right here is 54%. So the entire circle is 54%. For our play sports, this entire circle is going to be 62%. So we need to figure out how much are in each one. So this piece right here, this circle, but isn't included in the sports, is girls who don't play sports. Over here is going to be, so this is girls, not sports. This is not girls and plays sports. So we want to figure out the percentage of every single one of these pieces. So first, we know that half of the girls play sports. So half of 54% are girls who play sports. So that means inside here is 27%. Because half of those percentages of girls actually play sports, and that is this section right here. So then I need to also know girls that don't play sports. So girls who don't play sports is going to be a combination of 27 plus something to give me 54, and that's 27%. So these two need to add up to be the total number for my girls' circle itself. So then we can come over here, and we know that 62% play sports. So we already know that 27% are girls. So then over here, we just need 35% are not girls who play sports. So I added 27 and 35 to give me 62. Because again, I'm talking about this entire circle should be 62. So I'm just adding those things together. So then the last piece, so not girls and not play sports, this whole space needs to add up to 100%. So I just need to add up all of these and then subtract it from 100. So I get 11% are not girls and not play sports. So I got this number again by doing 100%, because that is the total space, minus the 27 plus 27 plus 35% to give me that 11%. So every single one of these should add up to 100%, and we were able to find each of these subsets. So then you can start asking yourself different kinds of questions. So they may ask you what percent of this school are not girls and they don't play sports, and that would be 11% of this school. And that's not something you may see right off the bat when you're looking at this 54 and this 62%. So making up this Venn diagram to help us look at these subsets of these two different options actually helps us visualize this problem a little bit better. Then we can do more information with this If we had, say, 1,000 kids, and I wanted to figure out, okay, how many of those 1,000 kids were girls who played sports, I just multiply that 1,000 by that 27%, and I get my number. So there's a bunch of different questions they could ask after this, but it's the setting up that is typically the hardest. All right. So the last one that we have is a tree diagram. So a tree diagram, we made one of those at the very beginning of this unit when we were doing our counting of how many ways we can arrange A, B, and C in different orders. So that was a tree diagram. So we can also make tree diagrams to help us with these multiplication principles of probability, because we can see the flow and we can actually multiply the branches together. So we have an example. It says 2 identical cookie jars are on a counter. So we have 2 cookie jars. So we have A and we have B. It says jar A contains 2 chocolate chip and 2 peanut butter. And jar B contains 1 chocolate chip. So it says, what is the probability that a chocolate chip cookie is randomly picked? So that means that you randomly picked one of these jars and then you picked one of the cookies out of that jar. What's the probability that it was a chocolate chip? So this may look complicated, but if you set it up as a tree diagram, it's actually fairly straightforward, because we can start looking at each individual problem separately. So at the beginning, we have 2 different choices. We could go and pick from jar A, or we can pick from jar B. So there are 2 different outcomes here. So the probability here is actually 1/2. There's 50% chance of you picking because you're randomly doing it. So it's either you're picking from jar A or you're picking from jar B. So then in jar A, let's look at it as chocolate chip and peanut butter. So for chocolate chip, we have 4 total, and there are 2 of those total which are good. Same for peanut butter. There's 4 total, and 2 of them which are in our event space. So I could figure out the probability for each of these lines. So all I have to do is multiply this 1/2 times this 1/2 to get me 1/4. This 1/2 times this 1/2 to also give me 1/4. So these are the probability of me picking a chocolate chip from jar A is actually just a 1/4 chance of it happening. Same with the probability of picking from jar A for peanut butter, also was just 1/4 of it happening. So then I can look at jar B's line. So for jar B, for a chocolate chip, there's only 1 chocolate chip and 1 event space. So here it's just 1/1. So 1/2 times 1/1 equals, do the little line again, 1/2. So the nice thing about doing this is that these totals should equal 1, because 1 is 100% of all the outcomes. So here, all I have to do now, if I wanted to figure out the probability of a chocolate chip, it's either this or this. Hopefully in geometry you remember the words and or. And means multiply your probabilities together if you said that word. Or means you add them. So since I can pick this chocolate chip cookie from this jar or this one over here, I just add 1/4 and 1/2 together, and I get that there is a 3/4 chance of me picking a chocolate chip cookie with all of this stuff happening. So that is a tree diagram. I hit my 30-minute mark again somehow. So if you have any questions at this point, I'm going to answer them. Your homework is posted on the website. Just do the first 15 problems. We still have some learning to do before you can do the next 15 or the next 10 problems. So just wait on problems 16 through 25 on the homework until we've gone over stuff. I think it's next Monday we'll go over. So again, I used my probability or my multiplication principle of probability to help me with this tree diagram, where I'm listing the probabilities of each event happening on their lines, and then I multiply straight across. So this could have a lot of lines, and all you have to do is just keep multiplying through all the branches, and you can see that at the end all of them should add up to 1. If they don't, you messed up somewhere. Okay. Again, if you have any questions, or be looking out right now. Otherwise, you can always message me on Remind, and I will help you with any questions you have on your homework. Alright, no questions, so good luck. So Kalia, we do have a test. It will be next Friday. We won't be having a final that I'm aware of. I don't think that they want us to be giving a final because of how long it would take, etc., etc. And honestly, I just don't want to give out any of those questions anyway because reasons that I'm sure you all can think of. But again, we will have a test next Friday, but no final. And seniors are basically done after that test. There'll be like one little assignment afterwards, but it's not something you have to worry about. So you should know your grades after that next test on next Friday.